Hi, my name is Xavier Leoté. I work for Confluent, and in my job, I basically deal with everything that's related to stream processing. And today, I kind of wanted to talk to you about how to troubleshoot your stream processing jobs in the context of Kafka. So just to get a little bit of an idea of the audience here, who here is running or has at least tried out Kafka before? All right, so good portion. Who here is running it in production? All right, let's say about 50% maybe. And are you guys running any Spark streaming jobs or any other stream processing applications on top of those? Who among you? Okay, good. So just to give you an idea, this talk will get pretty technical and we'll go pretty far in details into how to actually troubleshoot and some of those issues you may face when running any kind of stream processing job. It could be Spark streaming or just like your own Kafka applications against Kafka. But since this is Spark Summit, I kind of want to illustrate this more in the context of Spark streaming. So just a little bit of a recap. So if you're not familiar with Kafka, Kafka is a distributed, fault-tolerant, and scalable transaction log. It has offers certain guarantees in terms of partitioning, replication, and ordering. And the nice thing about Kafka is that all the consumers can consume at their own rate and advance it independently and even go back in time and replay the data, which is always nice when you do any kind of stream processing or need to restate some data. Some of the nice properties of Kafka it also offers exactly once semantics and transactional commits, which can be even more helpful when you try to do complex stream processing tasks. So in the context of this talk, the problem is a lot of people, when they think about, oh, what do I need to do to monitor my stream processing job, is that they imagine there's going to be all these metrics, all these things that they have to monitor. They have no idea where to start. And the reality that we've gained from the experience we gain from working with our customers is that in reality, it's much more, that people are much more often flying completely blind. They have no idea what metrics to look for. They have no monitoring, nothing, and they somehow expect that their stream monitoring is going to work. So I'm going to talk about some of our real-world customer experiences here. And the first case is going to center around how do I actually debug one of those broken stream processing jobs in Kafka, and how do I go about this? What are the steps that we typically walk our users through, our clients through, and also how I go about it, debugging my own stream processing applications. And the second part is more like an end-to-end use case, like try to look at all the pieces all the way from Kafka into your job and back into Kafka. How does it actually work? And to illustrate that, I wanted to take the most simple stream processing application you could possibly imagine, which is just replicating your data identically from one topic into another, or from one cluster into another one. That's as basic as any stream processing job will go, and I think that will be a good way to illustrate some of the things you need to look out for that are not just happening in your application. So typically, when we have someone going about debugging a stream processing job, they'd be like, well, somehow something stopped working. We don't know what. They'll seem to be happening, but we're not making any progress. And here's the checklist that we typically walk our users through. So here's all the things you kind of want to consider when you're looking at a stream processing application built on top of Kafka. So you have consumer lag, partition assignment, partition skew, client logs, GC logs, metrics. All those things are the basic things you really want to collect in order for us to actually be able to figure out what's happening and be able to identify where is the problem, what is going on in my stream processing job, and how do we go about fixing this. Because the reality is most people, when they face an issue like this, is they'll be like, GC log metrics, I have no idea how to get those. Let me just change some configs and restart the whole thing. And if you have tried that before, you usually know that doesn't go off too well. Usually they make the problem even worse, and then you don't even know where they started from. And then you have to debug not only the initial problem, but also the second problem that they created for themselves by changing all those configs. So the first thing I would tell people to look at when they're trying to debug their stream processing application in Kafka is to look at the consumer lag. So consumer lag is not going to tell you what the problem is. It's not going to tell you how bad the problem is. But if you see any kind of lag, it can help you identify where you may have some issues or what the issues might be. So it's not something you necessarily want to alert on because it's not some kind of SLA you can't define any kind of SLA around this metric, but it's something you can use to really dig into it. And for someone that's used or built any kind of Kafka application before, you'll know you have this concept of consumer groups. So the first thing you want to do is look at your consumer groups, kind of dump all the data that the group has. And the way you do this, you basically have this command line tool. There's other tools out there. Some have GUIs, some have not. But this is like the most basic, simple tool you can use to dump the information about your consumer group. And this will already tell you a lot of things about your stream processing application and what's going on. So the first thing you'll notice is this lag column. So this is what we're focusing on in the context of this debugging step, so to speak. We have the consumer lag. As you can see, we're about 40,000 messages behind on the first partition, and roughly the same on the second partition. And that by itself may not be bad, because if we're processing, let's say, 100 or 200,000 messages per second, that means we're only a fraction of a second behind on those partitions. What's a little bit more worrying is that we have a very high discrepancy on the last two partitions. And so the order of magnitude here is about 100x. And this is actually an example from a real-world application that I've used. I've just simplified the names of the topics and things like that, but this is an actual real-world case. And if you look a little bit more closely, you can see that we only have 3 consumer IDs on the right side. We have the last 2 partitions are assigned to the same consumer, which means that this is actually a case of bad capacity allocation. So this is an example of where you only had 3 threads or 3 workers, and they're all trying to consume 4 partitions, and it looks like they're not able to keep up. That last one is the way that the partitions were distributed across all the workers is that you had the first 2 only handle 1 partition, and the last one has to handle the remaining 2, because we only had 3 workers. And that means that once you're in a situation like that, your consumer is going to struggle if it's not able to keep up with the load that's and the amount of messages coming in. So that's an example of bad capacity allocation and how to identify that. The other thing you want to look at is your log n offset. So that one is important because you also want to make sure that the amount of data you're putting into every single partition into your topic is roughly the same. Because if that's not the case, then you can have the best capacity allocation, your best partition consumer allocation you want, you're not going to be able to have a good predictable load on each of your workers. So you also want to make sure that what you're writing into those topics is roughly evenly balanced. And in this case, we see like the order of magnitude is roughly the same, so we don't have a problem on that front. And the reason this is important is because not all partitions are created completely equal. So if you're familiar with Kafka, you may know that you can send messages to different partitions based on some kind of condition. What we call them is key topics. You basically key your messages and send them to specific partitions either by hashing the key or some other custom partitioning mechanism. And what you use that for is typically if you want to do any kind of processing of messages on a single worker. So if all the messages if a certain set of messages all need to be processed by the same worker, you will usually direct them to the same partition so that you can guarantee that they all end up on the same machine. So those key topics, those custom partition topics, will often exhibit an imbalance across partitions because you have to also take into account the nature of the data. So some of the early warning signs you might notice from having a problem like that is that you may only see some partitions lagging. So you may, like, only some of them are having a high lag. So like, similar to the problem we saw before, but in this case, it wouldn't necessarily be attributed to a single consumer trying to handle too many partitions. It would be because some of the partitions just have way too much data. The way you look for those things, look for signs, is by looking at your metrics, including uneven CPU and network usage, and those are usually telltale sign that something is off with your bounds. And the reason you might end up with those is because you have a skewed key distribution in your data. So let's say you're grouping things by customer ID, then let's say all those messages go to the same partition. If you have one customer that has a lot of messages, then you automatically going to end up with those cases where you have a lot of data in that partition. It's kind of similar to what people used to see back in the days of batch jobs and try to do any kind of group buys, and it would end up with all the keys in one partition. Or if you have nulls, like you say you're doing joins of data and somehow all the nulls end up in one partition. That's also a common case that we see when people do stream processing. And the last thing to consider is whether or not you have an imbalance across your brokers. And that's a little bit different because now we've ruled out any issues on the data side, we ruled out any capacity allocation problem on the client side. But it is still possible that you started out and you had 3 Kafka brokers and you created a bunch of partitions, a bunch of topics, and they were all nicely distributed. And then later on in the course of your scaling, you added more Kafka brokers, and let's say you scale from 3 to 7 brokers or something like that. But now your partitions that you initially created, they all still live on the same 3 brokers you had in the beginning. So they didn't get redistributed. And that's easy to forget. So people often end up saying like, oh, I added more machines to my Kafka cluster, and now my stream processing job is not doing any better. Or they may even have added partitions to that topic, but the initial ones are still on the same brokers, and now you have a very uneven distribution of those partitions on the Kafka brokers, which means the brokers themselves are now doing much more, some of them are doing a lot more work to push the data through than some of the newer allocated one. And the way you fix that kind of problem is by redistributing those partitions. There's tools out there, you can do it manually. There's some commercial tools available from Confluent as well to do that, basically allowing you to redistribute your partitions across all the brokers so that you have an even allocation across all your brokers. That's very important. So what about the client side? A lot of people forget that the Kafka clients actually have exposed metrics as well. And that's something that's a lot of people forget. It's not to say the most pretty way that they expose them is through like some form of JMX metrics. And it's not pretty, but at least it works, and it's pretty common for people to be able to ingest those metrics. The first thing you want to look at on the client side to rule out any problems in your application is to look at basic GC, CPU, network usage. Once you've kind of rolled out the basics, that's when you want to look deeper into the actual metrics of the Kafka clients. So the first thing you want to look at is, let's say you want to look at general slowness. What you want to find out is it on the consumer side or on the producer side? So typically your stream processing application will have, well, let's say take data from Kafka, do some processing, and then put it back into Kafka somewhere else. So you need to figure out, is it on the reading side or is it on the producing side that I'm having issues? Because it could be either, it could be both. So some of the metrics you want to look at on that front is the global request latency. So there's quite a few metrics related to request latencies on the Kafka client, and they're broken down by producer and consumer, so you can tell, am I at least seeing good latencies on the read and write side? Can I roll out any I/O issues, any network issues on both fronts? So that may not be enough because some partitions may not be lagging and some partitions may be, and you may not be able to detect that at the global request latency level, or certain things might be washed out in the averages. So what you can do from there is really look into per broker metrics. So the metrics on the client side are actually broken out by broker. So you can actually detect if it's a specific broker that's the problem, or is it a specific partition. So that's very important because you want to be able to tell, is it related to my data, or is it related to my hardware? Is it related to the node, or is it related to some configuration of the topic? The next thing is looking at the topic metric data. So here we can actually break out all those metrics by topic and identify which of those topics that I'm consuming is the problem. And that can help you determine whether you should be tuning the configuration of that topic, tuning the configuration of your clients for that particular topic. And that's information that's very useful to have. A lot of people often overlook the client metrics and never really look at them. But they're extremely valuable to debug those kind of situations. If you're still having some problems, the next thing we recommend is to turn up the log level. The problem is that sometimes we have clients that tell us, well, we added debug logs or trace logs, and now there were too much logs that we just deleted them. It's not very helpful because then we can't really fix the problem. So I would definitely recommend anytime you're seeing something that's happening on your Kafka client side that's not, where you feel there's something going on, turn up the log level at least to debug, especially on the producer side. The producer side is not very verbose in terms of how much logging it does. So you should definitely up the level on that one, maybe even to trace if you're having some gnarly issues on the Kafka side. So that's for logging. But sometimes we don't even have logs. We don't have any metrics. So what do we do in that case? Well, in that case, we have some actually pretty cool tools that allow us to do things online. So some of you may be familiar with flame graphs here. Anyone? At least a couple hands. So flame graphs are this pretty cool tool that was written by this guy called Brendan Gregg at Netflix. And they work hand in hand with some of the underlying Linux performance tools. And some folks combine that with some of the JVM internals and built this async profile tool, which basically is a very nice tool to be able to look at performance data both inside of your JVM, but also inside of your Linux kernel. So you can actually look across not only your JVM, what's happening inside of your JVM, but also look into what's happening in the kernel, in the I/O, and see if there's any kind of system calls that are taking up CPU. It's actually pretty simple. Once you've downloaded the async profiler, it actually includes the frame graphs, so you don't even need to download the frame graph tool. Once you run make and you install this, you can just run the profiler. What this does is basically I'm going to take 30 seconds of performance traces for this particular process ID and dump that into an SVG. And if you don't even want to do that, there's this really cool tool called Flamescoot at Netflix, which basically installs an agent on you can install this agent on all your machines, and then you can have a nice little web GUI and go over any period in time in the past and just drag and highlight a time period, and it will generate a flame graph for that time period for that particular application that you've been running on that server. So it's pretty nifty. And what the output looks like of this flame graph looks pretty cool, but it's actually also very useful. And this image doesn't really do it justice because it's actually interactive. So you can go in and really drill down into each of those stack frames and look at how much time you're spending in all the different parts of your streaming application. So just to explain what this graph is about, you have on the x-axis, this is your total CPU time. And the width of each of those bars is what percentage of the CPU, what percentage of the time on the CPU it's taken to run that particular function. And on the y-axis, you basically have the stack. So you're basically walking the stack, going from the lowest level where you have basically the JVM interpreter or the main JVM function calling into your code and running all the different parts. Everything that's yellow is JVM internals. Everything that's red is either native code or Java interpreter. And then at the top, we see some more with the native code. And then everything that's green in between, those are that's the actual Java application that you're running. So let's say in the case of Kafka client application or Spark streaming application, you would see a lot of that. And you can actually tell a lot of information from this chart once you kind of learn how to read it. The first thing is we notice is that we're actually spending roughly 20% of the time doing garbage collection. And this is actually a chart that was taken from an in-house application that we built that does some pretty heavy stream processing and actually also uses some RocksDB library to do some stateful processing. And I'll kind of walk through all the pieces we can identify. So 20% garbage collection, what that tells us is we're creating a lot of garbage. We might be creating a lot of short-lived objects. It may be a sign that we're spending a lot of time doing serialization and deserialization. That's pretty common in stream processing, but you have to be careful because that usually creates a lot of garbage. So that's one thing we want to look out for. The next thing is the RocksDB code. So this is all the native code that Java calls into to do any kind of RocksDB operations. So what this tells us is we're actually spending a lot of time, probably half of the time, just doing updates and reads in RocksDB in our streaming application. And so that probably tells us there's something we can do better here. Either we need to optimize the kind of operations we're doing, or we're doing some kind of expensive scan operations on the RocksDB database. So when you do any kind of stateful processing, it's very useful to not only have the Java side, but also have the native side, because if you just did a JVM profiler on this, you probably wouldn't be able to identify as easily what part of your code is actually taking time here. The next part you want to look at is the actual Kafka pull-up, and that's actually pretty small. It's not that small. I mean, it's a couple of percentage points, so we're definitely doing some work deserializing objects here, but it's not that bad. And the last bit is the actual processing time. So those three little pillars I pointed out, those are that's your application code. That's your business logic. Everything else is just overhead. So what this tells us is like we have a lot of room to make improvements in how we use our stream processing framework. We really need to understand how it works in order to make the best use out of it, because oftentimes it's not our code that's the problem. It's oftentimes how we use the framework or the libraries that we interact with. And I actually took an example just to be a bit more in line with the theme of the conference and try to have something that rings a bit closer to people's heart here. I took the actual Spark streaming clickstream example. It's in the actual downloadable Spark streaming distribution. And I modified that one to read and write to Kafka. So that's the only modification I made. It's pretty much the same code. So you can see the code is pretty short. I read from Kafka, take some page view data, group it by zip code and status, actually group it by zip code and to windows of a couple of seconds, and then print out the results. And keep some small, like some stats around that. And so I submitted this job to Spark in my test environment, and then did what I showed before, which is to run the profiler. And this was the result. We can see one good thing is we're not doing too much GC. That's the little sliver on the right, on the bottom. So at least GC is not a problem here. This part on the right is the scheduler event loop, so that's not really related to the code that we're running. Everything on the left-hand side, that's our task that's running. So we're focused on the left-hand side of the task running. First thing we have is the shuffle. So the shuffle, this middle part here, that's all the time we're spending reshuffling the data writing it to disk for the Spark streaming job to actually do the group by. We see that we're spending roughly 20% of our time doing that. And the next thing is we're spending 30% of our application time doing purely deserialization. So that's of course with the defaults. Like I'm just running this example out of the box, and I haven't optimized any of the deserialization, so this may not be as bad in a real production application. But a lot of people just, when they start with the examples and they write this first application, they're like, well, let me just take the example and write it as is and don't really think too much about it. But when you look at this, you realize that there's a lot of time spent just reading data from bytes into Java objects and vice versa. And here's again is our actual processing workload. And that includes reading from Kafka and doing the actual transformation that we care about. So I tried to find the actual functions calls that were from our actual code, and I had to dig really deep. And roughly, we're only spending maybe 0.2% of our time doing actual execution of the code I showed you before. Everything else is just happening in Spark streaming. Now, of course, this is a very simple example. It doesn't do very much. But that kind of goes to show how, like, where you have to look if something is not going very, very well. If things are feeling sluggish, feeling slow. It may not be in your code. It may be elsewhere, and maybe it's just you don't understand exactly how to use the framework properly. Maybe there's certain better things you can do around using better serialization formats. And those things are often easily overlooked. And I would say pretty much guaranteed across all the stream processing application I work with, once you get to a certain scale, I guarantee you serialization is going to be one of your top issues. And that's even more important if you have multiple steps. So if you have multiple workers that talk to each other, every time you need to go over the network, over the wire, anytime you need to write something to disk, you're going to face serialization and deserialization, and that becomes very expensive very quickly if you're not careful into how you structure your application. And as a last resort, of course, like if you've rolled out all of that, then maybe it's in your code. And just to illustrate some of the issues that we often see, some of the mistakes that a lot of beginners make when they write their first application in Kafka. And maybe that's not the case if you use some of the Spark streaming defaults, but once you get to a certain level, you start, and a certain scale, you have to start worrying about all the little details of how the data actually gets read and written into Kafka, because it matters a lot. So some of the things that people do very frequently is when they read their messages from Kafka, they'll read in one by one and commit one by one. Because somehow they're afraid that if they don't commit, they're going to have to start over again or have to reprocess a bunch of data. People are somehow afraid, or they don't know what to do with those commits. So they decide, well, I'm just going to commit every time I consume a message. They just don't know any better, so they just do that, and they don't really think about the consequences. The reality is when you commit a message in Kafka, it actually needs to round trip to the broker and tell it, like, look, I'm definitely done with this message. You don't have to send this message again to me. And that round trip is actually quite expensive. So the rule of thumb I tell people on how often they should be committing when they consume data from Kafka is to only do it as often as you need in order to keep your recovery time short. And what I mean by that is if your application crashes and you didn't commit the last batch that you consumed, what you want is when your application comes back up, that it will reprocess all the data from the last commit, and however much that is should not be too long for you in terms of what your application SLAs are. So you should only do it as often as needed so that you can maximize your throughput. So you can do it every couple seconds, every batch that you consume, or any time that you feel you've consumed enough that you don't want to lose that work. But at the same time, feel comfortable that if you were to lose that work, it's fine. It won't be too bad to restart from where we left off. And how do you validate those things? Well, there are metrics on the client side called commit rate and commit latency. And those are the metrics you can look at to see, am I actually committing at a reasonable rate? So the rate will tell you how often per second you are committing messages on your partitions. And then the latency will also tell you how expensive that commit is, because that will identify, like, well, how many milliseconds does it actually take for Kafka to acknowledge that I've received those messages. And that's important to understand for you to actually maximize your throughput. So that's on the consumer side. On the producer side, we kind of have a similar thing. So we have to right size our batches. So the Kafka producer, the way it works, is it will batch data for you. But you have to tell it how big those batches should be. And it will basically buffer those messages up until you reach a certain size or a certain number of messages, and then it will push them off into Kafka to maximize the throughput on that front. Of course, if you have bigger batches, that will improve your throughput. It will also improve your compression, because any compression that you apply in Kafka happens at the batch level. And typically, all the messages look very much alike. So if you only compress one message at a time, you're not going to gain very much. So if your batch size is 1, you don't gain very much from compression. But if your batch size is 100 or 1,000, and those messages look very much alike, especially if you use something like JSON or some of those formats that have schemas embedded in them, you will get an extremely high compression rate by increasing the batch size. Now, of course, you want to keep those batches small enough that it doesn't impact your performance. And a rough idea of what a good message size is anything smaller than 10 or much smaller than 10 megabytes is a good size, because when the data gets sent over the wire and the message gets consumed on the other side, you want to make sure that when that message goes through the Java heap or whatnot, or if it gets deserialized, it doesn't create too much garbage collection pressure. So messages should be kept relatively small so that we don't create too much garbage collection pressure. Now, there's two ways you can tune the batch size. One is, of course, batch size itself, which tells you, like, this is the maximum number of messages I want in my batch. But then there's this other setting called linear milliseconds. And what this tells the client is to say, like, I want you to wait at least this long before you send the message, which means that it will wait that long and wait for new messages to come in and buffer them before sending the batch. I promise you that setting by default is set to 0, which means that it will not wait. So unless you're producing messages at a high enough rate that you can fill those batches in under milliseconds, it will basically send only one message at a time. So for a typical application, you'll probably want to set this to 100 milliseconds or 200 milliseconds. It will add some latency to your application, but you'll get a very big improvement in terms of throughput, and you won't spend all your time just sending data. You can actually spend more of your CPU time doing actual computation. So the way you detect those kind of problems is looking at your request rate on the producer side, looking at your request latency, request latency. There's also a metric I forgot to put on the slide, which is the actual batch size. So it actually tells you what's the average batch size over the course of time. And then there's a compression rate. So you can actually use all those metrics on the client side to really tune and maximize your throughput on the producer side. So those are the two main things that I would say beginners struggle with, and here's some rule of thumbs for you to work off of. The next thing that people will often encounter is rebalancing. And the symptoms of that is that you have some very low throughput, there's a lot of network chatter, lots of network traffic. The consumers will dump tons of logs on you, but you're not making any progress in your stream processing application. Everything seems to be doing a lot of work, but kind of hanging. So on the data side, you're not making progress. And what rebalancing is the way that the Kafka client distributes the workload across all the different consumers. So just to recap how this works is that on the Kafka side, you have one topic which maybe consists of, let's say, 6 partitions. Those 6 partitions are going to be consumed by 2 consumers in the same consumer group. So the consumer group defines among which consumers you want to divvy up the workload. So let's say we start off with 2 consumers consuming 6 partitions. They each consume 3. Great, we've got a very nicely balanced workload. Now, if you have a new consumer join the group, and it's like, hey, hi, I want to join the group, I want to help out, do some work too. What happens is that this consumer will send a message to the broker and say, like, I want to join the group. And in return, the brokers will be like, okay, I'll stop sending any messages to anyone and tell the other consumers to also ask me to rejoin the group. So now they also have to say, like, hey, I want to rejoin the group as well. And then the broker will respond and be like, okay, you guys are all part of the group, and it will elect a leader among them. And like, you, consumer B, are now the leader for this group, and you're in charge of assigning who gets to consume which partitions. And as part of that response, it also gives it the list of all the consumers that are consuming, that want to consume the partitions of the topic. And the reason this is done on the client side is so that your application can actually customize the logic of how to distribute those partitions across all the different consumers. And that's very important if you have a very complicated workload, or you want to distribute the data in a very specific way, or you want to have some kind of host affinity of where the different partitions get consumed on which nodes. So that's why it's important to have this logic on the client side so the client can decide how that happens. Once that is decided, all the consumers will respond with a sync group request, and the leader will also include the assignment of which consumers will consume which partitions as part of this assignment. And in response, once they get the response from that, they will get a response from Kafka broker saying, you are assigned this set of partitions, and those are the ones you should be consuming. So once that whole process has completed, now we can finally continue consuming. So you can imagine, like, this process of allocating the partitions to all the different consumers is very expensive. It requires a lot of network round trips. It's very expensive, so you don't want this to happen very frequently. And the problem is that your application will start rebalancing if any time one of those consumers drops out, whether it's for network reasons or because it has some flaky hardware or is somehow busy doing something else and doesn't respond. Every time that happens and you have some of those nodes flip-flopping, it will cause this whole process to start, this whole cycle, rebalancing cycle to restart over and over again. And what you will notice, the way you can identify this problem is if you have any kind of long GC pauses, let's say tens of seconds, or if you forget to call pull on your consumer, because sometimes people have applications that don't consume very much data. Maybe it's one message every minute or so, so they don't think about calling pull. But the problem is if you don't call pull, then the Kafka client will think that your application is dead and somehow like, got stuck doing something else. And so it will actually drop it out of the group, and the whole cycle, rebalancing cycle, starts over again. So you'll have to make sure that you not only keep your GC pauses low, you also need to make sure you call pull frequently enough that doesn't happen. And maybe you want to increase your timeouts. So if you don't call pull very often, you may want to increase the timeout, the max timeout between pulls before Kafka decides that your application is dead. And also other things like any network-related timeouts, you probably want to make sure that they're not too short, especially if you're working in the cloud. We'll often see that networks are very flaky, and a single bad machine can affect the entire group and cause mayhem. So you want to make sure that your timeouts are long enough that you don't go too long without detecting failure, but at the same time, make sure you don't cause these kind of frequent rebalancing across all your groups. And the way you can detect those things pretty easily is just looking at the join rate and the sync rate. So the join rate will tell you how frequently you do those join group requests, and then the sync rate will tell you how often you're doing the sync group requests. So just watching those and seeing if you see any kind of high rates on that front, that usually indicates you have a problem, and you want to, you may want to look into any kind of hardware issues or making sure that there's not something that causes the consumer to be unresponsive for a certain amount of time. So as a recap, so if you're a competent user and you're a competent stream processing user, you want to monitor your consumer lag, look out for any partition skew, collect logs, obviously, and understand how to tune batch sizes. But once you become a Kafka Pro, that's when you also want to make sure you watch your group partition assignments, you monitor all your client metrics, you understand this consumer rebalancing, and understand how to profile your applications. And all of that is done so you can really distinguish whether the problem is on the client side, is it in your application, or is it on the broker side. That's really what it comes down to. I mean, identifying those, differentiating between those three pieces is key to being able to troubleshoot your problems. So now let's move on to the simple use case of just replication. So replicating is essentially the most simple stream processing job you could imagine. It doesn't do any work. It just takes a message from A and puts it into B. You just consume and you produce. Shouldn't be too hard, right? Well, this is a type of questions that our users face every day. Like we have a disaster, main cluster, we have to be able to fail over. We can't lose any more than 7 seconds of data. We have certain SLAs. Those are the kind of the questions that we're trying to answer here. Like how can we make sure that we're in a situation where we can fail over gracefully? And I talked to you about monitoring lag earlier, so monitoring your consumer lag. So that's one way of doing that. And here's another nice UI on top of consumer lag. But consumer lag, like I said, doesn't tell you very much about your application itself. It doesn't tell you how far behind you are. It won't tell you, am I 7 seconds behind or am I 2 hours behind? Because the number of messages may not be constant. It may be fluctuating. The rate of messages you're consuming could vary tremendously throughout the day, especially if you're consuming metrics data from various systems, or if you're consuming log data or request data. Those things tend to vary a lot. So you don't necessarily, even by looking at your consumer lag, you won't be able to tell how far behind you are. So what you want to do is, instead of looking just at consumer lag for those particular use cases, you want to look at your replication lag in seconds. So the way you do this, and there are some tools out there that do that for you, including this one. This is a nice one to look at, but there's other ones, there's open source ones as well you can use. They basically look at the messages you're producing, marking the timestamps there, and then looking at the messages you're consuming and looking at the timestamps there, and then correlating those, and then figuring out, well, what is the lag between your producers and your consumers? And that will allow you to tell you how far behind are we actually from consuming the data. And not just in terms of number of messages, but actually in terms of time lag. So we can tell, like, look, we're roughly 2 seconds behind on average. That should be good. We should be able to fail over. So that's what you want to look at when it comes to your SLAs. And those are the things we want to alert on if you have any kind of monitoring system. Because alerting just on lag is not going to be, it's going to be very noisy and honestly help you identify problems, especially if you have a period of slump where you don't produce too many messages. So the way that replication works, so if you think about how replication stream processing job works, you just take the data from the origin, buffer it in the consumer, send it down to the producer, block it when it's full, and write to the destination and acknowledge it. So at each of those steps, you can have something go wrong. And I'm kind of going to walk you through what you need to pay attention to and how you can identify the problem. So let's start with the destination side. So the producer is writing to some destination cluster, some topic. First thing you want to look at is your IO ratio and IO weight ratio, outgoing byte rates. This will tell you, like, how much time am I actually spending trying to push this data down into the destination cluster. Because if you start seeing issues there, then you know, okay, my destination cluster is a problem. The next size is, and I already talked a little bit about this, is the batch size. So that tells you, like, am I actually using my resources efficiently? What's the maximum size that I'm seeing? What's the average? Those are the metrics that will tell you in the producer side, like, am I actually using my resources efficiently, or is there a problem somewhere? Am I not seeing the batch size that I'm expecting? If my batches are too small, I'm not going to have the throughput that I want. Lots of things can go wrong. Next is the error rate. So once we actually send the messages, we also need to make sure that they get acknowledged. If there's an error, we're going to have to retry. So you want to keep an eye on the retries and the error rates on the destination side. Now, on the client-side application, basically the app that does the consuming and producing, you now want to look at anything that's waiting. So any waiting threads, any buffer pool wait times, all those things are indications that your application is somehow waiting on things. So we're not fully utilizing our resources here. Now, back to the consumer side, again, I/O is the main thing you should be concerned about. I mean, this is a very simple use case, and I'll stop for a picture at the end so you don't need to take pictures of every single step. Yeah, so the I/O ratio at the consumer side, again, tells you what percentage of the time am I waiting on I/O operations, and what is my consumption rate there. Then the counterpart to batch size is looking at the fetch size. How many messages am I getting every single time I'm calling poll? So am I getting a lot of them? Am I getting only some of them? So that tells us, am I really able to fill up that buffer and make good use of it? Or am I somehow not getting messages fast enough that I have to constantly poll the brokers for more data? And only then you should probably worry about the lag. I mean, all those things will, of course, interplay, but all those things are things you want to watch out for. And there you go. Now you can take a picture. Anyway, and again, to recap what we're talking about here, we're worrying about network and destination Kafka performance. We're worrying about making sure we have the right batch size, make sure there aren't any issues on the destination side, make sure there aren't any issues on the origin, and make sure we make good use of our bytes on the input. Yep. There we go. Now you can take a picture as well. So that's kind of a recap of all the different parts that are completely unrelated to the actual stream processing and business logic you're doing, but all things you have to worry about once you start reading and writing data from Kafka. Now the next level, and this is really if you want to go really deep into this, if you're doing any kind of work in cross data center operations, or if you need to have some kind of failover scenarios, you need to replicate the data. Now this is another whole can of worms, because if you want to send your data over a wide area network, you have to tune not only your application level, the Kafka clients, but you have to tune everything all the way down the stack, all the way down to the operating system. And the reason why that is that most Linux distributions and Kafka clients out of the box are tuned for networks, for local networks, and for applications that are running in a local cluster. They're not tuned to the applications across data centers. So not only you have to worry about your buffer sizes, you also have to worry about all your OS tuning, all those things. And there's some of those things you can take pictures of, and it'll be in the slides. They go really deeply into all those things if you really care about making sure you can get the most throughput out of it, because that's a whole different beast than doing it on a local network. So as a recap, our competent users will monitor consumer lag. They'll add processes when things are slow, automate their deployments. And the real pros not only look at the consumer lag, but they actually monitor time lag, collect their client metrics, and based on what I gave you, they'll know which side to blame. They'll know what configs you tune. They'll be able to tell you, like, it's on the destination side, it's on the source side. They'll be able to pinpoint really where the problem is. And lastly, like, you really want to get into that, also tune things over once. And if you have any more questions on how to do this, I mean, there's some more resources on Kafka and everything on our website. There's a neat little demo that kind of shows you all the different pieces. And lastly, I want to say thank you. And I'll open it up for questions.
So you explained the process of rebalancing. So what happened with the offsets when the rebalancing happens, and where do the consumer resume from?
So if you're rebalancing, the state of the application doesn't necessarily change. So you're not losing the state. The consumer still knows at what offset it is. So it is able to keep track of that. The problem is that state is stored in memory. So the issue only arises if your application actually crashes and goes down. Then you would have to start back at your last commit offset. But if you're doing any rebalancing, that happens independently of any offset committing. So if you have any rebalancing, you don't have to worry about consuming any of the messages you haven't committed so far.
How the new guy know about the offset?
That's more an implementation detail of the client, but as an application developer, you don't have to worry about those aspects. So we'll make sure that whatever it is at, and however it decides to rebalance the partitions, that the new consumers will pick up where they left off.